Hello, everybody out there in podcast land. This is Mr. Folly, and welcome to podcast 10.4. We're going to do phase diagrams, which are pretty straightforward. We're going to do vapor pressure and how that defines boiling, and then determine whether phase changes are exothermic or endothermic, and talk about our lab for the heat transfer of metals, which is later on this week. This is our last podcast. Yay! Phase diagram. So I thought I scribbled this stuff out, so I guess I'll scribble it out very quickly. So, whoops, here we go. Oh, come on. Come on, happy pen. Alright, pretend you don't see this. Whoa, whoa, whoa. Okay, let's look at some things now. The x-axis is temperature, and the y-axis is pressure. And what you'll notice is there are three different shaded areas, so there are three different states of matter. And you have to figure out what the states of matter are, solid, liquid, or gas. So if I'm trying to figure out which one I think is the solid I know is the coldest state of matter, so I'm going to be looking over here. And I know solids would be typically the most pressurized, so I'm going to look up here. So that must mean this, who knows what state of matter, what color that is, gray, green, whatever that is solid. Then I think of gases. Gases, I know, would be the ones with the least amount of pressure because they can fly all over the place. And gases, I know, are the hottest. So as I look over to the right, more and more and more and more, these are the hottest, so this must be the gas. And then that means the one left over must be a liquid. Okay. The other thing that's kind of interesting about this is you can tell where normally we talk about a boiling point or a freezing point or a sublimation point. This line right here, hopefully it's showing up better, this line right here that I put in green is the sublimation points. So really it's a sublimation line. This line right here is solid to liquid, which would be the melting point, freezing point. And then this one right here would be liquid to gas. So liquid to gas would be the boiling point. So that means instead of having one point, we have a line, which is a series of ordered pairs. There's a special pressure called 1 atmosphere, and that's the normal pressure at sea level. And at 1 atmosphere pressure, we would call this the normal melting point, boiling point, or whatever. And in this case, it's only going from a solid to a gas, so solid to a gas would be sublimation. So this would be the normal sublimation point. There is no normal melting point or boiling point for the substance, which is CO2. Okay. Anywhere on this point, we learned in our lab today, anywhere on this point there are both solids and gases. On this point there are solids and liquids on that line. This line there's liquids and gases. Both of them exist at the same time. Right here we have a special point where they all intersect, and it's called the triple point. It's where all three states of a matter exist at the same temperature and pressure. Okay. Over here, we have what's called a critical point. And that's the point where if it gets any hotter than the critical point, it must be gaseous. Okay. I know it's hard to read, but that word's gaseous. So anytime you're hotter than the critical point, you must be a gas. So let's see if I covered everything that I wanted to. Is melting point really a point? No, it's a line of ordered pairs, temperature, pressure. To find triple point, all three states of matter at equilibrium, meaning it can be any of them and go back and forth. To find critical point, any hotter must be gas. And then to find normal boiling point, that would be the boiling point at exactly 1 atmosphere. No matter what, the normal means 1 atmosphere. So even if you live on the top of a mountain where your pressure is not 1 atmosphere, the normal boiling point is still 1 atmosphere. An important point about this is boiling point changes with elevation. So let's pretend that we've got a giant valley, say Death Valley. And Death Valley, there's the bright sun that's always beating down on us, and it's survivor time. So we've got somebody down here in survivor land who's trying to survive in Death Valley. Now, Death Valley is really, 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 really deep. So remember, air pressure is dependent on the column of air beating down on your head. So if you're in Death Valley compared to being on Mount Kilimanjaro, the column of air beating down on your head is very different. So let's say there's someone we want to put in Death Valley. Who would we want to put into Death Valley? Okay, Sam is in Death Valley, and she sees a hunk of roadkill right here. That's blue roadkill, and she wants to cook it. So she's going to start a fire and cook it in a pot, and she's curious as to what the temperature is going to be when she cooks her roadkill. Do you think with this extra air pressure, as some water molecules try to turn into a gas and bust up, because all of these columns of air are beating it back down, the boiling point will be higher because the air particles right here are smashing it down. As soon as it tries to evaporate, bam, smashing it back down. Jump up, bam, smashing it down. So if the boiling point's higher, once she gets the water to boil, she can cook her armadillo for minutes, and it will be fully cooked. When she's later on in her little survival escapade, and she's got a little fire going on over here, same deal with a pot, cooking an armadillo. Then, because the air column is much, much shorter, it won't boil at 100. So this, when I said the boiling point would be higher in Death Valley, it might boil at 110. So it's like the oven you're cooking it in, the boiling water you're cooking it in is hotter, so it doesn't have to cook as long. On top of Mount Kilimanjaro, the boiling point might be 88 degrees Celsius. So if she wants to cook her armadillo and not get diseases, she'll have to cook it for, say, 15 minutes instead of 10. Okay. So elevation or atmospheric pressure changes the boiling point. Water has an odd phase diagram. The last phase diagram that we had a forward slope to the solid to liquid, the melting freezing point. Water doesn't have that. Water has a negative slope. That means if you put pressure on ice, it will melt. Okay. So, and you do need to know water. It's odd. I'm gonna say unique, but it's not really unique. It's unique for Chem Accel. Okay. It has a negative slope for the melting point. Ice expands, and the way I know this that affects me the most is I have to shovel my driveway, and where the cars have driven over the snow, it's crunched the snow. So what that causes is when you crunch the snow, you make it melt. So snow is easy to shovel. But when you crunch the snow and it becomes a liquid and then freezes, then you have to chisel away the ice. So when you have snow tracks, it's because you start off that stick on the ground to turn into ice. It's because you crunch the snow, it melts, and then refreezes. Ice floats, so that means that when you turn into a solid versus a liquid, if you compress it, so solid to liquid, the higher the pressure, the more compressed it is. So this means that a solid is less dense because it will exist with less pressure. And then we compared it to a normal one, which would look, okay, oops, let me do one. I'll make it red. A normal one still looks kind of like a Y, but it has a positive slope versus a negative slope. Vapor pressure. The pressure of an evaporated gas back on the liquid. So, container, liquid, make it look more liquidy. Some of these guys are going to evaporate. And if I put a lid on this container, if I put a lid on it, some of those guys that evaporated will hit the top and bounce back down. Right? So you get some coming up, some coming down, and you end up with an equilibrium, which is the vapor pressure. So the pressure of the evaporated gas back on the liquid in a closed container. Boiling, the definition of boiling. Vapor pressure equals atmospheric pressure. That is the definition of boiling. Sorry, of boiling. So that's why water will boil easier on Mount Kilimanjaro, because the atmospheric pressure is lower, so the vapor pressure needed is lower. And why it takes more in the bottom of Death Valley, because it takes more pressure, the atmospheric pressure is higher, so the vapor pressure must get higher. How can you make something boil cold? So if you just drop the pressure, so it will boil and the temperature won't change. So in space movies, if you're on the space shuttle, hope you like my space shuttle. I don't even know why it looks like this. Here's a little window. Got your little pot of water again. Woo! And you're going to dump your pot of water out of the space shuttle. What happens is, as soon as you throw the water out, because the pressure in space is 0, then that means that the particles will boil right away, which is pretty cool. Phase changes are energy changes. So as you go from a solid to a liquid, it's endothermic, because liquid has higher energy. This would be lower. So it's endothermic because it has to absorb energy. Solids have lower energy, absorb energy to become liquid. Or you can think of it as you have to break solid bonds. And breaking bonds, of course, endothermic bonds are broken. Liquid to gas, big endothermic, because you have to break liquid-liquid bonds. And they change so much because there's so much space in between them, and they go through those things. So it's a big endothermic reaction. Gas to liquid, I'm going to get rid of that now. Gas to liquid is a big exothermic change, and so it releases a lot of energy because liquid-liquid bonds form. And there's a huge change between one gas particle over here shooting around doing its own thing, one over here shooting its own thing, and then when they have to actually come all the way together, so come all the way together and form a bond. Woo! That's a ton of energy that must be changed to do that. And then liquid to solid is exothermic. The liquid must release energy to become a solid. And exothermic bonds are broken. Our lab we're going to do in a couple of days. We're going to heat up a metal cylinder in boiling water and get its temperature to about 100 degrees Celsius. We learned that water doesn't really boil at 100 in class today. We're going to have a styrofoam cup with cool water, which is really room temperature, 25 degrees Celsius. So we're comparing 100 degrees Celsius to 25 degrees Celsius. Put the hot metal in the cool water, and what will happen from our little online lab, the metal will get colder, and the water will get hotter, and we'll talk about that. So the hot metal gives heat to the cool water. It loses heat, which would be a negative sign, and cold water gains heat, which is a positive sign. Heat is Q. So, and again here we're not changing states of matter. So hot metal has a negative Q, and cold water has a positive Q. Remember, Q equals mc delta T. So my metal is losing heat, so it's got a negative Q. So negative mc delta T equals positive mc delta T. And the temperature change in the metal is going to be final minus initial. So T sub F minus 100. And this would be T sub F minus 25-ish, whatever the temperature of the water is. Okay, final minus initial. And your final temperatures will be the same. You're going to weigh it. That's how you get this. You're going to weigh this. Specific heat of water is 1 calorie. And specific heat of the metal is what we're going to solve for. So this we can measure with a thermometer. Errors in this lab. You have to explain the errors. You want all of your heat from the metal go to the water. Where will the metal lose heat besides the cool water? You take it out with tongs. It's going to touch the tongs. It's going to touch the cup. And those things will take heat away from it that don't go into the water. If you lose heat, what does that do to the calculated C of the metal? If you lose heat, that means that the temperature of the water, the change in temperature will be too small. So it's going to look like not as much heat transferred. So that means that it's going to look like the C of metal is too small. So change temperature is too small. So Q is too small. So when I look at it in terms of the metal, Q equals mc delta T. This is for the metal. If Q is too small, that would mean that C would be too small. Phase diagrams are a Y. Temperature is the x-axis, pressure is the Y. What I mean by a Y is something that looks like that. Think of the extremes to ID it. So solids are high pressure and cold, gases are low pressure and hot, and then liquids left over. Water has a different slope. Make sure that you know that. Vapor pressure affects boiling point and sublimation. Hot things burn, but steam burns more because changing from a gas to a liquid is lots of energy. Changing temperature is some energy. Changing state is lots of energy. Steam burns more because it goes from a gas to a liquid, which is ginormously painful. Have a good one. Try not to be ginormously painful, and I'll see you tomorrow.